Hey y'all, today what we're going to do is we're going to introduce our next unit. This unit's going to focus on how atoms interact with each other to form things called bonds, which form compounds, and how those compounds will interact with each other in things called interparticle forces. So our focus this unit is going to be heavily based around Coulombs Law. Now, if you remember Coulombs Law, you'll remember that it is a force of attraction between two charged particles is proportional to the charge divided by the distance. Remember that this is not an exact equation that I'm presenting to you. Remember that this equation is simplified to just show proportions. I don't expect you guys to be able to calculate the exact force of attraction using Coulomb's law, but as long as you remember and understand that the relative charge is predicated on the effective nuclear charge of an atom, and the relative distance is based on the number of energy levels, that's where we're going to start. As we move through this unit, we're actually going to somewhat adjust Coulomb's law based on the context of what we're looking at. But in general, if you remember that the Coulomb's law proportions are based off of the relative charge, which is effective nuclear charge, and the number of energy levels in an atom, you're going to be just fine. So let's start by talking about what is bonding. Now, bonding is the interaction between two atoms, specifically the nuclei of one atom and the valence electrons of another atom, and the nuclei of that other atom with the valence electrons of the first atom. So in other words, there's a mutual attraction for valence electrons of each atom. What that does is creates a more stable, and this is key, a more stable configuration than each atom was in previously. So essentially, we can think of bonding from a probability standpoint, based on thermochemistry. Thermochemistry was always talking about essentially how the more stable position, the position with lower potential energy, is the more likely position to be in. It's more thermodynamically favorable. Well, bonding is all about thermodynamic favorability. To create a bond is to create an attractive force. And so when we create that attractive force, we're doing so using probability. What this means is that atoms, which have very similar chemical characteristics, which means they're in the same periodic table group, are going to bond in very similar ways. So if we look at the most simple configurations of bonding, we're going to split into three categories: molecular or covalent, ionic, and metallic. So we're going to split into three categories initially. So let's talk about each of these three categories first. Let's start by talking about covalent or molecular bonding. In covalent or molecular bonding, we have the interactions between two nonmetal atoms. Nonmetals, by their nature, tend to be smaller, so fewer energy levels, and have higher effective nuclear charges, right? So if we look at the periodic table, they're in the top right corner of the periodic table. What this means is that they have a relatively strong attraction on valence electrons, but not just their own valence electrons, but also the valence electrons of other atoms within interactions. So what this means is that two nonmetals are going to be relatively attracted to each other's valence electrons. And this is all based on Coulomb's law. So if we think about a nonmetal, it's not going to readily lose electrons, but it will accept in general. It will pull electrons towards it. Now, if you have two atoms playing this game of tug of war, two nonmetals tend to be fairly even. Not always perfectly even. We're going to talk about that in a little bit, but relatively even. What does this mean? Well, it means that the electrons, the valence electrons specifically between the two atoms, are going to end up what we call shared. Shared is not a perfect way of thinking about it, though, because it's not like the electrons are just going to be sitting there right in the middle of the two atoms. What's really happening in a covalent bond is that the electron cloud that surrounds each of the two nuclei is going to be transformed into a new shape. This means that there's going to be an area of greater electron density between the two atoms. That's the covalent bond. It's the region of higher electron density between the two nuclei. Ionic bonds, meanwhile, are not going to be taking place in the same way. In an ionic bond, we pair an atom that has lower a force of attraction on its valence electrons, a metal, and a nonmetal, which has a relatively high attraction on valence electrons, and we pair them together. Now, metals, by their nature, remember, metallic character is the ability to lose electrons, or the ease with which an atom loses electrons. So if we have a metal in the pair, it's going to more readily give up electrons. It has a lower Coulombic force of attraction on its valence electrons. The nonmetal, meanwhile, is going to have a relatively high Coulombic force of attraction on its valence electrons, and thereby the valence electrons of the metal. This is why we think of an ionic bond as one where electrons are transferred completely from one nucleus to another, from the metallic nucleus to the nonmetal's nucleus. This creates a totally different type of bond structure. Metallic bonds are our third category of bond. Now, in metallic bonds, none of the nuclei are relatively attracted to valence electrons because they're metals. All of them are. And in metals, what's going to happen is electrons are more readily lost. In this case, we end up with what's called a sea of electrons, where electrons are only loosely attracted to each individual nucleus within this metal, but attracted sufficiently such that we can actually provide a configuration of what we consider a bond. Because of this loosely attracted electron configuration to the nuclei, metallic bonding has a very unique set of properties, one which we're going to get into here in a little bit. So let's wrap up and summarize this video. In the end, what you need to walk away with is that there are three major categories of bonding: covalent or molecular bonding, ionic bonding, and metallic bonding. The three differ simply in the structures of the atoms and their relative interactions with the electrons, the valence electrons specifically, of another atom. So if you look at the three, they're really on a spectrum. They're on a spectrum because of the fact that nonmetals and metals all have different Coulombic forces of attraction on their valence electrons. So in covalent bonding, you're dealing with two atoms that are relatively strongly attracted to valence electrons because of high effective nuclear charge and fewer number of energy levels. In ionic bonding, it's generally one atom which is going to be highly attracted to the valence electrons, while the other atom, the metal, is less attracted to the valence electrons. Therefore, there is the incomplete sharing or stealing, if you will, of a valence electron. And finally, with metallic bonding, because they're all metals involved, relatively speaking, none of them are exceptionally attracted to the valence electrons, and therefore the electrons kind of move throughout the substance, and as a result, we end up with what's called the sea of electrons. Remember that in compounds that are made of elements from the same groups tend to have similar configurations, but also similar properties, just like the elements themselves have similar configurations and similar properties. And again, all that comes down to valence electrons and their overall electron configurations in the valence shell. Also, keep in mind that Coulombs Law plays a huge role throughout this unit. Please make sure that you are aware that Coulombs Law is a big deal. And if you're not already familiar with Coulombs Law, you should go back to our original unit, our summer unit, and review Coulombs Law from that unit. So that wraps up today's video. Thanks for watching, and I'll see you in the next one.